Chapter 13 Electric Field. In this third video, we will explain the work done by electric force, electric potential, and electric potential energy. Let us recall the relation between electric force and the electric field. E equal F over Q. E is the electric field, F is the electric force, and Q is the charge. Instead of electric force, KQ source times Q over R square times 1 over Q, and we get KQ source over R square. So force equal KQ, Q over R square. So the electric force depend on both the source charge and the test charge, while electric field depends only on the source charge. If I have a positive source charge, the electric field is centrifugal, and we can experience at any point electric field. And if we have a negative source charge that has centripetal electric field, we will experience an electric field on a point within its field. While if I have a positive source charge and we have a tested charge, then of course we have electric field on this point. But since we have a tested charge, then this tested charge will experience an electric force. And if this tested charge is negative, then the force will be opposite to the electric field and we'll have attraction force. Work done by a constant electric force. If we have two parallel plates connected to a battery, then one of them will be positively charged and the second will be negatively charged. We will experience a uniform electric field between the two plates, starting from the positive going towards the negative. For simplicity, we will represent the electric field by only one arrow. If we introduce an electric charge at point A between the two plates, and we move this charge to the negative plate to point B, of course charge Q is experience an electric force F in the same direction as the electric field. And this electric force is parallel to the electric field, making an angle alpha with AB. We can notice from the geometry of the figure that AA prime is adjacent to alpha. Thus AA prime is AB, the hypotenuse, times cosine alpha. So now we can write the expression of the work as we all know, work equal force dot distance. So here the distance is AB, then work equal force dot AB. We can solve the dot product, F times AB cosine alpha. But as we notice from the geometry of the figure that AB times cosine alpha equal to AA prime. And also we know that F equal QE. So let us substitute them in the equation. We will get QE instead of F and AA prime instead of AB cosine alpha. And thus work equal QE times D. But we all know that E times D is voltage, since E equal U over D. Voltage over distance. This is the electric field. And thus work equal Q times UAB, which is potential difference between A and B, and W equal Q into VA minus VB. Thus the work done by an electric force while a charge moving from A to B is F dot AB, which is Q UAB, the potential difference between these 2 points. If we have a positive charge between the two plates, initially at the positive plate, it will experience an electric force parallel to the electric field, and the charge will accelerate toward the negative plate. And we notice that the charge is moving in the same direction as the electric force. And since Q is positive and the potential difference is also positive, then the work done by the electric force from A to B is also positive, and we call it motive work. But if I force this positive charge to move from the negative plate up to the positive plate, its motion is opposite to the electric force. And since I'm moving from B to A, I will use the potential difference UBA, which is negative now. So here the charge is positive, but UBA is negative. Since now the work done by F not from A to B, from B to A, and so F dot not AB, BA equal to Q times not UAB, it will be UBA. And here we notice that UBA is negative. So if UBA is negative, then Q times UBA, positive times negative, the work will be negative. and we call it resistive work, since the electric force is opposite to the displacement. Now, if I have a negative charge particle initially at the negative plate, it will experience an electric force opposite to the electric field, since it's a negative charge. And here the negative charge will accelerate toward the positive plate. Here the charge is moving from B to A. Thus the work done by electric force from B to A equal to Q times UBA. But as we notice, Q is negative and also UBA is negative. Thus negative times negative, the work is positive, and we call it a motive work. Since the electric force is behind the movement of this charge, so we call it motive work. But what if I force this charge to go back to the plate? Now the motion in the opposite direction of the electric force. So the work done by the electric force now will be negative. Since the charge is negative, but I'm moving from A to B, which is UAB, and this voltage is positive, then negative times positive will be negative. And now the work done by electric force is resistive work. Since the electric force is trying to resist my motion, and by using a very nice trick, we can derive a new unit for energy. We all know that the unit of work is joule, then 1 joule equal the unit of charge is coulomb, and the unit of the voltage is volt. So 1 joule equal to 1 coulomb volt. Of course, I can multiply both sides with any number I need. So let us multiply both sides by 1.6 times 10 to the power minus 19. Of course, this is the trick we are using. So 1.6 times 10 to the power minus 19 joules equal to 1.6 times 10 to the power minus 19 coulomb volt. But you can remember that the fundamental charge E equal to 1.6 times 10 to the power minus 19 coulomb. So instead of 1.6 times 10 to the power minus 19 coulomb, I will put E. So we will get 1.6 times 10 to the power minus 19 joules equal 1 electron volt. And this electron volt is the new unit for energy. While dealing with nuclear physics and small energies, we will use this unit. 1 electron volt equal 1.6 times 10 to the power minus 19 joules. Of course, it will be given in the problems. What we mean by equipotential surface? Again, these two parallel plates, positive and negative plates. And let us take C and the same negative plate as B. And as we said, the potential difference between A and B, UAB equal to E dot AB. So E times AB times cosine 0, since the angle between electric field and AB is 0, then E dot AB equal to E dot D, the distance between the two plates. Let us try to calculate UAC. UAC is the electric field dot AC now, since the distance AC. And we solve the dot product, E times AC times cosine alpha. But we can write from the geometry of the figure that AB, which is adjacent to alpha, is equal to AC cosine alpha. Thus, instead of AC cosine alpha, I can write AB, and AB is D, so it is equal to E times D. So UAB equal to UAC equal to E dot D. Thus, VA minus VB equal to VA minus VC. So we can conclude that VB, the electric potential of the point B, is equal to the electric potential of point C. So B and C are equipotential, and the plate is called equipotential surface. And of course, the potential difference between B and C will be 0. E dot BC. E and BC are perpendicular. So E times BC times cosine 90, which is 0, since cosine 90 is 0. We can see it on the figure. CB is perpendicular to the electric field. So E dot UBC is E times UBC times cosine 90. The angle between BC and E is 90. Then the work done by the electric force, if the charge moves from B to C, equal to Q times UBC, which is 0 joules. Similar to the work done by mg whenever we are moving in a horizontal plane. Here also the electric field is perpendicular to the path from B to C, thus the work of the electric field is 0 joules. So here we can say B and C are equipotential since they are at the same equipotential surface. Also A and D are equipotential since they are at the same equipotential surface. And if I have this line parallel to the plates, also it is equipotential surface. So M and L are equipotential. Also another parallel line, N and R are equipotential. Also here, S and K are equipotential. As we move from the positive plate towards the negative plate, the electric potential will decrease. The positive plate is the high potential and the negative plate is a low potential. So electric potential of A is greater than the electric potential of M. And as we move away from A, the electric potential is decreasing till we reach the electric potential at B. So electric potential decreases while moving with the electric field. Here if we have two parallel plates, the red is the positive and the blue is the negative plate. If I have this particle here, any 2 points at this level has electric potential 8 volt. And any point at this level has electric potential minus 4 volt. The red points are equipotential and also the blue points are equipotential. Let us recall gravitational potential energy and the kinetic energy. Whenever I have a ball at a height h, this ball has a gravitational potential energy since it's available in a gravitational field. And if we release this ball, this gravitational potential energy change into kinetic energy. We can see here the man at a height h and has a gravitational potential energy. Zero kinetic since he's at rest. Now if he jumps, his potential energy now becomes zero. And while jumping, we can recognize that the kinetic energy is increasing, while the gravitational potential energy decreases. But if I raise him up, I'm giving him potential energy. Here the work done by mg is negative. The mg is a resistive force now. While if the man jumps, the kinetic energy is increasing while the gravitational potential energy is decreasing. And the work done by the weight is motive, it's positive. Always if we release the man, he will move toward the ground to decrease his potential energy. While this ball is falling now, the weight is doing emotive work. Work by mg is mg height initial minus height final. Of course, it's emotive work since the height final is 0, then height initial is greater than height final, and the work done by mg is positive. And the ball is losing gravitational potential energy, thus the variation of gravitational potential energy is negative. It's decreasing. And we all know the relation work done by mg is the opposite of the variation of gravitational potential energy. If the work done by the weight is motive, then the gravitational potential energy is decreasing. While if the work done by the weight is resistive, the gravitational potential energy is increasing. We all know the relation of gravitational potential energy is m times g times h, mass times gravity times the height. Of course, the height with respect to a reference. Let us try to conclude the electric potential energy formula from the gravitational potential energy. Instead of the mass, we can write Q, the charge. Instead of the gravitational field, we write the electrical field. And instead of the height, we will use the distance. So electric potential energy is QED. And instead of ED, we can write also the potential difference U. Here, as we have more height from the reference, we have more gravitational potential energy. And as we go closer to the reference, then the gravitational potential energy decreases till it reaches to 0 whenever I'm at the reference. So the work done by mg equal to mg times height initial minus height final. This is the work done by the weight. And the variation of gravitational potential energy final minus gravitational potential energy initial, which is equal to minus the work done by mg. Also electric potential energy. If we are dealing with positive charge, it has more electric potential energy when it is far from the negative plate. And as it reaches the negative plate, then its electric potential energy becomes 0. Here, if we have a negative charge, as it is far from the positive plate, it has the higher electric potential energy. And as it moves toward the positive plate, its potential energy decreases. So the tested charge moves to decrease its electric potential energy. Positive charge moves from high potential to low potential. Negative charge moves from low potential to high potential. Here the negative charge will move from the low potential to the high potential, While if we have a positive charge, it will move from the high potential to the low potential. And also its electric potential energy decreases till it becomes zero at the negative plate. Here if we have a negative charge, it will go from the low potential to high potential and decreases its electric potential energy. So if the work done by F from A to B is QUAB, work done by electric force, then the variation in the electric potential energy is electric potential energy at B final minus electric potential energy at A initial. Electric potential energy B equal to Q electric potential B minus electric potential at A equal to QVA. I can take common factor the minus, then I will have the variation in electric potential energy equal to minus into QVA, now it's positive, minus QVB, so it is minus Q into VA minus VB, which is the potential difference between A and B. And we will get the same result as the variation of gravitational potential energy and the work done by MEG. The variation of electric potential energy equal to the minus of the work done by the electric force from A to B. As we know, electric force is kq q over d square. Electric potential energy equal to the force times the distance. So it will become kqq over d. So force and electric potential energy depend on both source charge and test charge. While E equal to kq source over d square and potential difference equal to E times d, which is kq over d. And electric field and electric potential depend only on the source charge. Application 3. Two parallel plates separated by a distance d equals 0.5 meter are connected across a DC power supply that maintains between its terminals a potential difference of UBA equal 1000 volt. Given the charge of electron is minus 1.6 times 10 to the power minus 19 coulomb and the mass of the electron is 9.1 times 10 to the power minus 31 kilogram. D and C are 2 points between the two plates such that DC is 10 cm and BD is 30 cm. These are the two plates connected across a battery of 1000 volt. These are the 2 points D and C separated by 10 cm and dB is 30 cm. Part 1. Calculate the magnitude and write the expression of the electric field between the two plates. Take x-axis to the left and y-axis upward. So here we can take the x-axis to the left. This is my x-axis and the y-axis upward. So in part 1 they need electric field equal to U over D, the voltage across the distance. The voltage is 1000 volt and the distance 0.5 meters, the distance between the two plates. And the answer will be 2000 volt per meter. As we know that the electric field coming from the positive plate towards the negative plate, so it is in the same direction as y-axis. E is directed upward from positive plate to the negative plate, so E equal 2000 J, Newton per coulomb or volt per meter. These are the two units for the electric field. So part 2a, determine the potential difference UBD and UBC. UBD equal to E dot BD. And since E and BD are both vertical upward, then the angle between them 0. So UBD equal E 2000, BD is 0.3. We convert it from centimeter, 30 centimeter to 0.3 meter, equal to 600 volt. UBC equal to E dot BC. This is my BC. We can calculate BC using Pythagoras theorem and the angle also using the lines. But there is an easier way. Instead of BC, we can write BD plus DC. So E dot BD plus DC, and I can write E dot BD plus E dot DC. E dot BD, already we wrote it. E times BD times cosine 0, while E times DC times cosine 90, since E and DC are perpendicular. Here DC is horizontal and E is vertical, then they are perpendicular. This is 0, we cancel all this term, and the answer will be 600 volt. Part 2b. Calculate UDC by 3 different methods. Here the 2 points D and C. I want to calculate the potential difference between them. But as we noticed, they are equipotential, then the voltage must be 0. So we will calculate it by three methods. We already calculated UBD equals 600 volt and UBC equal to 600 volt. So first method, UDC equal to UDB plus UBC. UDB is minus 600 since opposite to BD, and BC is also 600, so minus 600 plus 600 equal to 0 volt. Second method, UDC is equal to E dot DC, means E times DC times cosine 90, which is also 0 since cosine 90 is 0. The third method, we can say that D and C are located on equipotential surface. So VD equal to VC, electric potential of D equal to electric potential of C. Thus the potential difference between D and C is VD minus VC equal to 0 volt. Now part 3a. Calculate in electron volt and in joules the work done by the electric force acting on the electron as it moves from the negative plate to the positive plate. So the work done by the electric force from A to B is equal to Q times UAB. We have an electron, then Q is minus the fundamental charge, and the voltage UAB is minus 1000. Since A is the negative plate and B is the positive plate, so UAB is negative minus 1000 volt. So we can write the work equal to 1000 electron volt. Let us calculate it in joules. Q times UAB, Q is minus 1.6 times 10 to the power minus 19 coulomb, times the UAB is minus 1000 volt. Then the answer will be minus times minus plus 1.6 times 10 to the power minus 16 joules. Part 3b. Deduce the variation of the electric potential energy of the electric field system as the electron moves from the negative plate to the positive plate. We know that the variation of electric potential energy is the opposite of the work done by F from A to B. So delta electric potential energy equal to minus W, which is minus 1.6 times 10 to the power minus 16 joules. Part 4. Compare the magnitudes of the weight of the electron and the electric force acting on the electron. The weight equal mass times gravity. The mass is 9.1 times 10 to the power minus 31 kilogram times 10 Newton per kilogram. The answer will be 9.1 times 10 to the power minus 30 Newton. As we all know now, the magnitude of the electric force is F equal to QE. But of course, remember that since we are calculating the magnitude of the force, the Q should be absolute. So F equal 1.6 times 10 to the power minus 19 coulomb, Q is negative but absolute, I took the positive value, times E 2000 volt per meter, and the answer will be 3.2 times 10 to the power minus 16 Newton. The weight of the electron is neglected relative to the magnitude of the electric force acting on it. Since this is the force 10 to the power minus 16, here 10 to the power minus 30. Since F is so huge comparing to the weight. Part 5. The electron starts from rest at the negative plate. Apply the work energy theorem to determine the speed of which the electron reaches the positive plate. Note, neglect the work done by its weight. Before applying work energy theorem, we should find the forces. So the forces acting on the electron is the electric force F only, since we neglect its weight. So apply work energy theorem, delta kinetic energy equal to the summation of the work done by external forces. We have only the electric force, so kinetic energy final minus kinetic energy initial equal to the work done by electric force F. Kinetic energy final half mv final square minus kinetic energy initial 0 since it starts from rest, and the work done by F is 1.6 times 10 to the power minus 16 joules. Then V final equal to radical 2 times 1.6 times 10 to the power minus 16 over the mass is 9.1 times 10 to the power minus 31. So approximately the velocity will be 1.9 times 10 to the power 7 meter per second. Let us do an application of moving of a charged particle in a uniform electric field between the two plates. Application 4. An electron P of charge Q equal minus 1.6 times 10 to the power minus 19 coulomb and mass 9.1 times 10 to the power minus 31 kilogram is given a horizontal velocity of magnitude V0 1 times 10 to the power 7 meter per second at point O, halfway between the two parallel horizontal metal plates. The plates are of length BB prime equal to 10 cm separated by a distance BA 5 cm. And connected across the terminals of a DC battery of voltage UAB 120 volt and we neglect the weight of the electron. Part 1. Determine the equation of the trajectory of the electron. As we can notice, whenever the electron enters to the electric field between the two plates, it will move in a parabolic trajectory. To determine the equation of the trajectory of the electron, we will apply the technique of projectile. Here I have the electron with initial velocity, horizontal velocity. All the initial velocity is along x-axis, no y component for initial velocity. Whenever the electron enters to the electric field, an electric force will be applied on it, pulling it toward the positive plate. So let us start by applying the forces on the electron, which is the electric force only, since we neglect the weight of the electron. So apply Newton's second law, summation of forces equal to ma. The only force is electric force, which is equal to QE equal to ma. Let us make projection along x-axis. The electric field is vertical downward while the y-axis is upward and the x-axis to the right. QE is 0 equal to max, thus ax is 0 meter per second square. So no acceleration along x-axis. Projection along y-axis, E is opposite to y-axis, then it's minus QE equal to may, thus ay equal to minus QE over m. Let us calculate E. E equal to U over D. The voltage is 120 volt and the distance is 5 centimeter, which is 0.05 meter. Then electric field is 2400 volt per meter. Let us calculate AY. So AY equal minus into Q is an electron, so minus 1.6 times 10 to the power minus 19 times 2400 for the electric field over 9.1 times 10 to the power minus 31, the mass of the electron. And the answer is 4.2 times 10 to the power 14 meter per second square. So we can write now the vector of the acceleration. A vector equals 0I plus 4.2 times 10 to the power 14 j meter per second square. Now we have the acceleration, we can calculate the velocity. Velocity is the integral of a with respect to time. So I will split the velocity to its components, Vx and Vy. So Vx equal the integral of ax dt and Vy is the integral of ay dt. Let us plug ax and ay. Ax is 0, then it is 0 plus a constant which is v0x. And the integral of ay is ayt plus a constant which is v0y. As we said, the initial velocity is horizontal, then it's equal to the v0x, while v0y is 0. So vx equal to v0, which is 1 times 10 to the power 7, while vy is 4.2 times 10 to the power 14. This is ayt plus 0. And now I can write the expression for the velocity, 1 times 10 to the power 7 I plus 4.2 times 10 to the power 14 tj meter per second. So now we have the velocity, we can calculate the position vector r. So r is the integral of v with respect to time. We split also the position vector into its component x and y. So x is the integral of vx dt and y is the integral of vy dt. Vx equal to v0, then it's v0t plus a constant which is x0. Vy is ayt dt. Ayt integral is half ayt square plus a constant which is y0. Let us plug the numbers. R equal, x is v0t, which is 1 times 10 to the power 7 t meter.
Y equal half.
Ay is 4.2 times 10 to the power 14 t square plus y0 is 0. Thus it is 2.1 times 10 to the power 14 t square. And the expression for the position vector is 1 times 10 to the power 7 ti plus 2.1 times 10 to the power 14 t square j. Now I have the expression for position vector x and y. From x I can calculate the expression for time, t equal x over 1 times 10 to the power 7. So let us substitute t in y. So y equal 2.1 times 10 to the power 14 t square. Instead of t square I will put x over 1 times 10 to the power 7 all square. Y equal 2.1 x square. This is the equation of the trajectory. And it is the equation of a parabola similar to this. A is 2.1, B is 0, and C is 0.
Part 2.
Deduce that the electron leaves the plates at a point I, indicate the coordinates of I. We should prove that the electron will move and will not collide with the plate. It will leave the plates at point I and continue its motion. we can see here that the abscissa of I is A prime, which is the length of the plate. So at I, x equal to L equal to A prime equal 10 centimeter, and it is 0.1 meter. Replace x by its value in y. So y is 2.1 x square. Instead of x, I will put 0.1, then it is 0.021 meter or 2.1 centimeter. In order the electron to leave the plate, its ordinate should be between 0 and 2.5 centimeter. And as we saw, its ordinate is 2.1 centimeter, which is within this range. Thus, electron P leaves the plates at point I. And the coordinates of I is 10 centimeter, the abscissa, and 2.1 centimeter, the ordinate. Part 3.
Deduce the
Leaving speed vi of the electron. Of course, we have the expression of the velocity, but we need the time. So the time needed by the electron to reach point I is, the time is x over 1 times 10 to the power 7. The abscissa of I is L, which is A prime. So 0.1 over 1 times 10 to the power 7 equal 1 times 10 to the power minus 8 seconds. Let us substitute the time in the velocity. So velocity equal 1 times 10 to the power 7 I, this is a constant, independent of time, plus 4.2 times 10 to the power 14 t j. Here I will plug the time 1 times 10 to the power minus 8. So it will be 4.2 times 10 to the power 14 times 1 times 10 to the power minus 8 j. And the answer will be velocity vector equal 1 times 10 to the power 7 I plus 0.42 times 10 to the power 7 j. We can now calculate the magnitude of the velocity by using Pythagoras theorem. V equal radical Vx square plus Vy square, 1 times 10 to the power 7 square plus 0.42 times 10 to the power 7 square. The answer will be 1.1 times 10 to the power 7 meter per second.